Because in section 5, we're going to start combining everything that we've been talking about. Right back there, I thought. So, continuity. The concept of, which we always talk about, f of x is a function that is continuous on some open or closed interval, blah, 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 blah. So continuity is very important for a lot of our theorems. For example, could we have taken any of our limits if it wasn't continuous? Or do the limits exist if the function is not continuous at all points?
No.
Give me some examples where it's not continuous. Well, let me give you this, the graph we have in our first one. We have at 1, at 2, at 1, 2, 4.
Two, and 4. And
Well, first off, let's remember, is the function continuous? No, obviously not, no. What is the domain that we're dealing with? Zero to 4. We start here, go all the way over. So we see that at what values? At 1, at 2, and at 4. Something weird happens. In other words, in algebra, we discuss continuity as being able to draw the graph without ever lifting your pen. That's not possible in this case. Actually, in this graph, you're kind of like a sewing machine. So it's not going to happen. What do we notice happens at x equals 1? What do we notice? Because there's an open circle there, and it starts out somewhere else, we call that a jump discontinuity. It's discontinuous at 1, so the graph jumps to a new location. Because on one side, it's connected to the graph, and the other side is connected to the graph. How is that different than at 2 and 4? At x equals 2, and also x equals 4, is it a jump discontinuity? No. What do we call that one? That's a removable discontinuity. Two and 4, yeah. How can you tell the difference? Look at the two differences here. The difference between a jump discontinuity as opposed to a removable discontinuity.
still like a continuous line run point with fixed points.
Right, because the line is continuous at the same location, but at that one point, it's jumps to another point. It's continuous, but then it jumps to another point. A jump discontinuity, it has at both directions, starts and stops at different places. And a removable discontinuity, how do you get a removable discontinuity? Removable discontinuity. A removable discontinuity is something like this. Oop. So what value can I not use in my graph? No. -2, because I can't have 0 on the bottom. So x cannot equal -2. But if I take this equation, I can factor out the top as x plus 2, x minus 2. The reason they call it a removable discontinuity is because I removed the discontinuity. Once those are gone, all I have left is x minus 2. So I cannot go to -2. So the graph would look like something like this. At -2, the graph would exist. But then we'd have a hole. So whenever you have a hole, and then what we do, we take this number, plug it into this, and that would give us our dot. Yes.
Is that why in finding the limit of a function that looks like that, you have to factor that?
Always factor in first, yeah. Is because if you have any discontinuities, if you have a rational expression, you automatically have a asymptote at the bottom. To see if that's a removable discontinuity, factor the top and see if anything cancels. If it cancels, great. Then we have something like this. We have a hole in the graph that it jumps to somewhere else. That we take our point we can't use, plug it into our simplified equation, and then that gives us our dot. So that's the difference between a removable and a jump discontinuity.
What if you had a line that did go straight up to connect it? Does that?
You can't. Then it wouldn't be a function. It'd fail the vertical line test. Because remember, these have to be functions. So the next section we're going to talk about are numbers at which the graph of our function has breaks. We have two types of points that we talk about in a domain, in a function. We say that our function f of x is defined on some closed interval. Here's A, here's B, and there's our function. These are called the endpoints. These are called the endpoints. And anything else inside there are called interior points. So in our graph here, does the limit exist at the endpoints?
For the posterior points.
No, I'm looking at the endpoints. The endpoints are at 0 and 4. Does the limit exist at the two endpoints? In other words, as we're getting closer to 0, is the graph approaching a certain number? Yes, the limit is 1. As we're approaching 4 from the left, is the graph approaching a number? Yeah, it's approaching 1 also. Because remember, limit doesn't have to be there, even though the value is at 1/2. The limit of this function is 1. How about the interior points? At 1, does the limit exist? Let me ask you again. At 1, does the limit exist? Because remember, for a limit to exist, at the endpoints, we can only do it from one side. Everything, all the interior points has to have limits from both sides. All interior points, the limit has to exist from both directions. So at 1, the limit as x approaches 1 from the left of our function equals what? As x approaches 1 from the left, it equals what? 0. As x approaches 1 from the right of our function, it equals, well, you have the graph in front of you, yeah? 1. So are they the same values? Nope. So the limit doesn't exist at 1. The limit value, it fails because there's a jump. So f of x is discontinuous at x equals 1. Because the two limit values do not agree, it's discontinuous at that point. How about now the next one we have to look at is at x equals 2. So as the limit as x approaches 2 from the left equals what? As x approaches 2 from the left, what does it equal? 1. Because as all our values, when x goes from 1 to 2, they all equal 1. So the limit as x approaches 2 from the left is 1. And likewise, the limit as x approaches 2 from the right of our function still equals 1. So what does that tell us? The limit exists, but is it continuous at that point? No, because of the removable discontinuity. The limits exist, but the continuity doesn't exist because of the jump discontinuity,
So
of the removable.
If it didn't have that removal, we could say yes.
Yeah, in other words, if there was an open slot, so it is not continuous. Continuous at x equals 2. How about x equals 4? And this one, we can only approach the 4 from the left. What does that value equal? Well, yeah, because look at the graph. This is the graph. Where is it approaching? It's approaching 1. Is that the value of f of x at 4? No, because at 4, the value is 1/2. So it's not continuous. Even though the limit exists. So because we see these breaks, this jump and these breaks, we say that the function is not continuous.
Is there any difference between x equaling 2 and x equaling 4? Because x equals 2 is in the middle of,
Well, yes, actually, a good question. Yes, there is. Because at x equals 2, it's an interior point. We have to take the limit from both sides. And since 4 is an endpoint, we only take it from one side. It's there's other than that, it's not much difference. Is the limit exists at both of them, but the values are removable as continuities. Yes. Ah, good question. An open circle means it doesn't exist at that point. For example, in graphing notations, if I gave you this, what this means in graphing, it means in interval notation, which means my answer set would be what this one says is I can go infinitely close to 2, but not use 2. This one is 5 is included. So that's what the open circle means. Open circles means do not include. Closed circle means include or included. Numbers at which the graph of f of x has no breaks. What about if we had f of x going to 3 as x goes to 3? What if we had the limit as x goes to 3 of f of x? Yeah, what would it equal? Yeah. As x approaches 3 from both sides, where is it approaching? 2. So as we're approaching the interior point. But because f of 3 also equals 2, the function is continuous at x equals 3. That's important. You notice how the other ones, they were not, they were not continuous, they were discontinuous. Either because of jump discontinuity or a removable discontinuity.
If X equals 3.
Then it wouldn't be continuous because f of 3 would not equal the same. If the limit and the value are the same value, then you know it's a continuous line there. So that's why in the interior points at 2, 1 and 2, it didn't work because even though we had the limit as x approaches 2, it didn't equal f at 2. The limit was 1, but f at 2 is 2. This equaled 1 and this equaled 2. That's why it's not continuous at that point. Let's look at the endpoints. The limit as x approaches 0 from which side? From the right. Was it equal? It equals 1. What is f at 0? Also 1. So that's the exact sign of its continuity at that endpoint. Unlike the limit as x approaches 4 from the left, does it also equal f of 4?
No,
This is 1 and this is 1/2. So yeah, it's not continuous at that point. So now let's define continuity. We have examples, we've looked at them. Let's define continuity.
function and what X equals are the same,
Yes.
but what they don't.
Then it's the discontinuity there somewhere. It's either a jump or a movable. Because that's the only type we've discussed so far. Basically, and if it's a rational expression, it doesn't have to be either of jump or it's an asymptote, which you can go to infinity both ways. So definition. Let's C be a real number that is either an interior point or an endpoint. Of an interval in the domain of F. Of the function. Let's look at that part, what that means first. Because every part of a theorem of a definition is important. Let C be a real number that is either an interior point or an endpoint. What does that mean? Yeah, has to be because the domain is between A and B. C is a point that could be either these endpoints or anything in the middle. So it has to exist somewhere in the domain of the function. So it's either an interior on the interval of the domain of the function. So it has to be defined. The x values have to be defined in that domain. Then the function f of x is continuous at that value c if a couple things occur. If the limit as x approaches c of f of x equals f of c. That statement right there means two things. If then the function is continuous at the point c, if the limit of that function as x approaches c equals f of c. So it means that the limit has to exist. The limit has to exist. The value has to exist, and they have to be the same. If that happens at any c on the domain, then it's a continuous function. Now let's look at the right and left-sided limits. Then the function f of x is right continuous at c if the limit of our function as x approaches c from the right is equal to f of c.
But that one would be.
An endpoint.
Yeah, as it went to 0 equal 1, 0 equal 1 on the graph.
Right. Yes. So if it's a right hand if it's on from the right, or it's the left endpoint, the minimum point, the function is left continuous at c if the limit as x approaches c from the left of our function equals that value from the left that we're getting to.
So the graph that we have is not left continuous because.
It goes
f
to
of x is 1, but
the function is 1/4 or 1/2, yeah. So let's look at here. These are the interior points. These are your exterior points. Interior points have to be continuous, so it has to be true from both directions. The endpoints are only one-sided limits. So these also exist for interior points, because for every interior point, you have to make sure that they're continuous from the left and from the right. So our example, you can say that the function is continuous except at 1, 2, and 4. In other words, there's your exception. If you want to prove that it's continuous, tell me some exceptions, but it's not continuous over the entire domain. Yeah, I'll try to stretch that theorem there. So f of x is a continuous function on some closed interval if three things happen. What are they? One, it is right continuous at point A. Left continuous at point B. And continuous at every interior point. So if there is one point where it's not continuous, you just state that. You're saying that the function is not continuous at this X value. Example 2. The function f of x equals square root of 4 minus x squared. What can you tell me about that? What domain are we looking at? Right. So our domain is -2, +2. So we have to look at x equals -2, x equals +2, and x is any point within -2, +2. Or you say that. The limits have to exist. So for -2, as x approaches -2 from the right, does the limit exist? Yes, equals 0. As x approaches +2 from the left, does this function exist? Does the limit exist? It's also 0. And as x approaches, let's say even 0, does this function exist? Equals 2. Okay, the limits exist. So it tells us that's a first condition for continuity. How do we test continuity? Well, plug them in there. At f of 0, at f of -2, we get 0. At f of +2, we get 0. And at f of 0, we get 2. Because at any point inside there, we can try those. So it tells us that the function is continuous on the domain of -2, 2. For those of you who haven't noticed yet, that's our visitor that we've had for some time, from -2 to 2, 2, our half circle. Let's look at example 3. Well, let's look at the greatest integer function. We're only going to look at it from -1 to 1 in our domain -1 to 1. Remember, we have three things to look at. The limit as x approaches -1 from the right of our function. Was it equal? -1. So at f of -1, the answer is -1. The limit as x approaches +1 from the left equals what? +1. Because as it approaches what? It's what is f of 1? It doesn't exist because it's an open circle. What is f of 1? No, because it's open circle. Nothing. Doesn't exist. There is no value for 1. We could say that if it was a greatest integer function, it would start off in the next level. But no. But in our domain, it doesn't exist. And 3, at any interior point, does it exist? At any interior point, does it exist?
Does that fall in the,
Remember, for any interior point to be continuous, you have to look at, I have to look at this. The limit as x approaches 0 from the left. The limit as x approaches 0 from the right. In order to have a limit, it has to have both of those, and they have to be the same. So as I'm approaching 0 from the left, what is it? No, it's always 0. The limit is whatever the values are. It's 0. When x approaches 0 from the right, it's 1. So because they're different values, at that interior point, it doesn't exist. There is a jump discontinuity. At 0. So it's not continuous. So the function is only continuous where it passes these tests. So it's continuous on this interval. It's continuous on this interval. It's just not continuous at the center, at the interior point 0. So here's, as it says here, at an interior point or an endpoint of an interval in its domain, a function is continuous at point where it passes what we just did, the following tests. This is called the continuity test. This is called the continuity test. A function f of x is continuous at a point x equals c if and only if it meets these conditions. This means if and only if. First, f of c exists. Where c is a point inside the interval. It could be the endpoint or it could be inside the interval. Two, the limit as x approaches c of f of x exists. And the limit as x approaches c of our function has to equal f of x. In other words, these two have to be the same. F of c has to exist. The limit as x approaches c has to exist, and they have to be the same value. Like we did at when x equals 3. When as x goes to 3, it equal 2. When x equals 3, it equal 2. So it was continuous at that point. Example 4. The function f of x equals the, I just did this one for y'all. Is this continuous? Is it right continuous or left continuous? At the integers? No, because remember with the graph of, this is the greatest integer function. That's what it looks like. So let's check these things. So at f of 1, does it exist?
Yes.
It equals what? 1. F of 1, it equals 1. That's the first one. Does the limit as x approaches 1 of our function, does that exist? No, because from the left, it's 0. From the right, it's 1. 0 or 1. Are they the same? No. So it's not continuous. The function 3x plus 2 on the interval -2, 2. Is it continuous? What does this graph look like? It's a linear equation. Yeah, it's linear because x has no exponents, no, it's not fraction or anything. So the y-intercept is 2. The slope up 3, 1, 2, 3, and over 1. So from -2 to 2, any value I pick, let's say I'm looking at 0. Does f of 0 exist? Yes, it equals 2. Does the limit as x approaches 0 exist? When you do this, you have to look at both from the right and from the left. And they have to be the same. As the graph from the right approaches, it's going to 2. From the left, it's approaching 2. Are they the same? Yes. So the function is continuous. So any value I pick between in this domain of -2, 2, it's going to give me a continuity function. So whenever you check the limit part, you have to check the upper and the lower limits. And they all have to be the same. If any one of the numbers are different, then it's not continuous. Because if these two numbers are different, then the limit does not exist. Therefore, it fails the continuity test. So these two have to be the same, and it has to match the point at that. Therefore, it's continuous. Examples where a function can fail to be continuous. So the example we just had up there. That's an example of a continuous function. How can we tell? Are all the points defined on the graph? Yes. So here's an example where it's not. There's an example there where it's not. Because there's a jump discontinuity or a hole, it's discontinuous. Or even if this point doesn't exist, even if I just had that, I don't have to have a value. It's discontinuous.
We'll say it's step at, or is it?
Yeah, you can say that, yes. But here we're looking at examples where the function fails to be continuous. It fails, yes, at this point here, at that C, it fails. So those are the most common ones because this occurs when you can remove a discontinuity. This one just occurs when we have, for example, 1 over, let's say 1 over x. That's an example. Well, that's not a straight line. Because this is whenever you have an asymptote of some sort. If you have a removable discontinuity, then you'll have a point that exists somewhere. What's another example? Well, there's another example where it fails to be continuous. Rational functions. The Atari symbol. This is 1 over x squared. It's discontinuous where? Yeah, because x cannot equal 0, so it's discontinuous at x equals 0. We also can say it has this right here. We have an infinite discontinuity. Because your discontinuities can go to infinity. They don't always have to go to a point.
Now, is that something you could say as it approaches 0, or just because x is not equal to 0?
Well, just because because the endpoints go to infinity, it's infinite discontinuity. But what we would say as x approaches 0 from the right, the limit goes to infinity. As x approaches 0 from the left, the limit goes to infinity. Conversely, let's say we had the 1 over x function. It looks like this. As x approaches 0 from the left, the limit approaches negative infinity. As x approaches 0 from the right, the limit approaches positive infinity.
Now, do the other ends play?
Ah, good question. Have we talked about those? As x goes to infinity, what happens? We haven't talked about those yet, but you open that can of worms. What happens when x goes to infinity? Where's the function going? To what number? 0. Yep, very good. Because we're looking at as x gets further away, what value are these numbers getting towards? They're getting close to 0. X is going to infinity. The limit goes to 0. Likewise, as x goes to negative infinity, the function goes to 0. Because remember, this has to be a y value. As x goes to infinity, the y values are getting closer to the 0. And then we looked at the earlier ones, we had the sine 1 over x function. The one that has the sporadic, where you can't tell where it's approaching, +1, -1. It's where it can approach and then something like that. So where you can't determine what's going to happen, it goes from -1 to 1. Who knows what's going to happen? So what do you know about continuous functions now? Continuous functions have to have what to be true? Has to be continuous. So how do we prove if it's continuous? The endpoints have to exist. The value at each interior point has to exist. And then for them to exist, the limits have to exist, and they have to be the same values. So for interior points, we have to look at both directions. For endpoints, we only look at one side, and they always have to be the same. So if it's not continuous, it's discontinuous. Example 5. Again, I just let that answer out a second ago. The function f of x equals 1 over x. Is this a continuous function? What does 1 over x look like? Where these all go. So is this a continuous function? The answer is yes. Because remember how we define continuity. F of x is a continuous function on its domain. What is the domain of this function? Negative infinity to 0, and then from 0 to positive infinity. Because x cannot be used, or 0 cannot be used. It's because 0 will make it undefined. It's an asymptote. So since on our domain, the function is defined, it's continuous. Because x equals 0 is not in the domain. So be careful when a question asks you, is it continuous or not? You have to first look at define the domain that the function is dealing with, unless it's given to you already. But if I asked you, is f of x equal 1 over x on the interval -2, 2 continuous? Is f of x equal 1 over x on that domain, is it continuous? Look at the numbers inside here. Look at the interior points. Can all of the interior points be used on this function? No, it's a rational. So what is our asymptote? Do we have an asymptote here? When x equals 0, the function's undefined. Is 0 inside that domain? Yes, it's between -2 and 2. So since I specify this domain, so the answer in this case would be no. Because I specified a domain. Unlike up here, I never specified the domain. I said, here's the function. Is it continuous?
Well, what if you specify the domain that is 0, but you still say yes?
Well, yeah, if I said from 1 to 50, it's continuous then. Because the only value I cannot use is 0.
Now, I understand if you use the hard points of 2, up to and including -2. But if you,
Even if I had open parentheses, it wouldn't matter because I cannot use 0 on that function.
would it matter your other choice of domain then? Well, because well, no, it's 0.
Well, yeah, if it's as long as I don't use 0, everything else works. Even if it's an open interval, doesn't matter. Theorem 8. properties of continuous functions. Again, the function f of x is continuous at any value c in an interval if that then the following hold. The sum rule. If f of x plus g of x f of x and g of x are continuous functions. If f of x and g of x are both continuous and I add them together, then they're both, then the sum's gonna be continuous. The difference, f of x minus g of x, will also be continuous. Because all you're doing is subtracting two values, not creating an undefined function. Constant multiple, or it's n times f of x. If f of x is a continuous function and I just multiply it by some scalar, some number, all it does is change the values. It's still going to be continuous. Actually, the way we should have done it is n cross f of x.
Oh, sorry.
The product rule, f of x times g of x. Again, if there are two continuous functions already, then it's going to end up the product being a continuous function. Then we have the quotient, which says f of x divided by g of x, as long as g of whatever value c does not equal 0. So this is the functions, but if there's a value c inside that domain where it makes the bottom equal 0, we can't use it. The exponential rule. So if we have a function raised to a power, all that's going to do is raise the exponentiate the y values. In the radical. So if I have an nth root radical function of this function, of course, now since we're dealing with nth root, if it's an odd root, it doesn't matter. The function could be positive or negative or 0. If it's an even root, you can only have 0 or positive numbers. So again, it depends on the domain you're dealing with. Let's see examples. So though, again, have we seen these different rules before? The sum, the product, the difference. Yeah, it's all the time going to be the same stuff. We're gonna talk about it over and over and over in different scenarios. Example 6, let's look how this works. For every polynomial, P of X, an, xn, an minus 1, xn minus 1, plus dot, dot, dot. Oh, wow, it's almost time to go. A1, A0. So because of that, we know it's going to work. So because as x approaches c of any polynomial, just plug the value in. Remember I said last time is to test if a limit works, just plug the value in, see if it works. If it works, great. If it doesn't, then we have issues. And the quotient, same thing. If P and Q are polynomials, then the limit as x approaches c, as long as those values are defined, again, for continuity, you have to make sure the c value doesn't violate the denominator. Make it equal 0. Ready to go? All right. Example 7. What if we have the absolute value of x? As x approaches c, the absolute value of x. Whenever you test these things for a value of c, you have 3 types of values to test. C is less than 0, C is greater than 0, and C equals 0. Because you have to check if they're negative, they're positive, or 0. Do they all work? If they all work, then it's continuous. So can I put negative numbers in there? Can I put like the limit as x approaches -3? What's the answer going to be? 3. The limit as x approaches +3 equals the limit as x approaches 0 is 0. As long as these values exist, that means the limit's continuous. And any value c we put in there, it'll work. How about trig functions? How about trig functions, sine and cosine? Do those exist? Yeah. Because there are no values c I could put in there that'll make it undefined. If I put pi/2, if c is equal to pi/2, then it equals 1. If it equals pi, then it's 0. And so on and so forth. Same thing with cosine. The limit as x approaches c of cosine of x, the same thing. We're bounded between -1 and 1. We'll pick up here next time because we have to discuss now inverse functions as well. So we'll pick up on that on Monday. So remember, starting next week, we're gonna meet 4 days a week. That way we can finish up faster.